Next up on deck is Paul Francis with a configuration-only approach to shrinking FIBs. Thank you.
Hi, I'm Paul Francis from Cornell. So the thing I'm going to talk about today is it's something we call virtual aggregation, but basically it's a technique by which a single individual ISP, without coordinating with anybody else, can reduce the size of their FIB just through a series of configuration tricks on their routers. Specifically, it reduces the FIB size and the ribs on the routers, but it doesn't reduce the rib size on route reflectors, as you'll see. But the idea here is that any ISPs that are coming up against having to upgrade their routers because they're running out of FIB space, rather than do that, can do the kind of configuration I'm going to show you, and put off the time at which you have to update your routers to however long, or to when you have to upgrade them for other reasons, and so on. So I'm going to start with just a couple slides. First, I want to tell you the status of this work. It's really a bit premature. In fact, the reason I'm giving this talk is that there's a lot of details, and in fact, there's multiple ways you can do this. And although we've managed to actually configure one of them on a set of routers, specifically some routers from the Wisconsin whale test bed, it's a very small-scale configuration, and it's just one of what I suspect are many ways to do this, and by no means the best way to do this. So we have set this up on a small scale, but we have a lot more work to do. And really what I'm here for is to try to convince a few of you who are interested in this and who really understand router configuration to help us out. I mean, my student, pores over the manuals and stuff to try to figure out ways to do this. It takes them hours and hours, and I think there's plenty of people in this room who could probably tell me in 5 minutes the best way to go about this. So in addition to the limited experiments we've done on actual configurations, we've done some modeling based on data from a large ISP. I'll show you a little bit of those results. But that's where we're at so far. There's a lot more work to be done, and again, I'm trying to solicit your help. So as I say here, we have not tested on a live network. We've not tested with a lot of dynamics, routers going up and down. We've not tested at large scale. So there could be a lot of issues remaining that we have to get through. And just in the interest of full disclosure, Cornell does have some IPR on the stuff I'm going to show you. Okay, so basically I've said this already. I'm looking for some router management gurus among you who are interested in this to work with us. And so I'll be here all day today. I'll be here all day tomorrow. I won't be here on Wednesday. So what I'd really like to do is just get a small group of people together who can come up with sort of a best practices kind of thing. And then maybe at the next NANOG, I'll be able to present something a little more settled. Okay, so I'm just going to whip through the ideas of this at a very high level, not the specific details, in part because there's many details to be worked out. And there's really three important aspects to it, so I'm just going to go through them. So what we're actually doing in this, like I said, we're not shrinking the rib per se, and we're not shrinking it on route reflectors, we're just shrinking it on routers. And what we're doing to do that is we're basically taking the DFZ table and we're partitioning it among the routers that you already have. So I show here, a kind of high-level picture, but it shows some POPs and shows some routers in their POPs, and they're connected in some way. And the idea really is the following. So again, it's called virtual aggregation. We take the IP address space, v4, v6, it will work equally with both. We partition it into virtual prefixes. So you can think of this as /7s, although it doesn't have to be /7s, and each ISP could pick their own virtual prefixes. But basically, you create these virtual prefixes, and then you assign each one to different routers, and then you run that set of routers as essentially a VPN for that virtual prefix. Okay, so with the result that what every router knows instead of the entire DFZ is it knows all the prefixes within its virtual prefixes, so the prefixes that it has to know today, but only within its virtual prefixes, and then it has routes, /7s or whatever, to routers that are covering the other virtual prefixes. Okay, so sort of taking the last rather busy picture here and throwing away the purple and red VPNs, just focus on the green VPN. A packet from some site to, say, a customer whose address is in the green VPN or the green virtual prefix would go like this. So it would start the normal way. The site would default the packet up to its ISP. Notice, by the way, that the green site doesn't have to be connected to a router that's doing virtual aggregation on the green address space. It can be attached to any router. Anyway, so the packet goes up to that ISP in the middle, reaches a router. That router, which is a purple router, doesn't have the subprefixes for that virtual prefix, but it routes the packet to a green router that does, just through normal BGP aggregation. That green router, having run, routing within the VPN, tunnels it to the green router in the destination POP, and then from there it actually goes tunneled layer 2 out the ISP to the neighbor. Okay. So you'll have already noticed that path length can increase as a result of this, and router load can increase as a result of that. And I'll talk about this thing in a bit. The path length is not so bad if you have a router covering every virtual prefix in every POP, but if you take one away, like in this picture, the lower POP no longer has a green router, then the path can be quite a bit longer. Okay? All right. So that's really issue number one. That's how we chop up the address space, and we're creating a logical hierarchy that aggregates better than the current physical hierarchy. The second issue is this one, right? You have most of your routers are border routers. I've claimed that an ISP can do this independent of the other ISPs, so the implication is that you're actually exchanging full routing tables across the border, and that's true. If each of these routers is only responsible for a small portion of the address space, then it breaks if they have to peer with the whole address space to their neighbors. So what we do is basically we exploit the fact that routers are both layer 2 and layer 3 devices at some level, and we configure things like this. So we basically set up a route reflector. The route reflector has a layer 2 path to the neighbor routers, and the full routing table is run with the route reflector. Then the route reflector does filtering and aggregation and sends the prefixes for the right aggregates to the appropriate routers, pretty much as shown here. Okay? It's not multi-hop. It's just routing at layer 2, although I suppose it could actually be multi-hop. And then we use the BGP next hop aggregate to make the packets go to the right place. So, for instance, we have a neighbor router who, in this case, is advertising a prefix 5.6/16. It goes to the route reflector with a next hop of 2222. The route reflector, in this case, sends it off to the red router, but it maintains the next hop as 2222. And so when the red router has to send a packet that's exiting to 2.2.2.2, it can actually ship that purely over layer 2, so it tunnels through the green router without the green router having to have those actual FIB entries. Okay? So that's part 2. That's really how you deal with other routers at the border. And keep in mind, actually, that both of these ISPs can be doing this. They would just be exchanging the full routing table with each other. Okay. Then the third part of this is dealing with the fact that we're increasing latency and we're increasing router load. And basically what we're doing here, and this is really the ugliest part of the whole thing, I suppose, is that we're exploiting the fact that there's basically a power law in traffic distribution. 90% of your traffic goes to 10% of your prefixes. So what we're doing basically is we take popular prefixes that have a lot of traffic, and we just spread them to all routers natively so that those packets take normal shortest path routing as today. And as a result, most of your traffic is native. A small percentage of your traffic is following these virtual aggregation paths, but that doesn't result in much load. I have a few results, but let me just show you this particular one. So latency actually works out extremely well. And this stuff is really in a way pessimistic. But if you look at this lower graph, basically what we're showing is the increase that an ISP would see in load if they deployed virtual aggregation today, and the FIBs continue to grow as they're projected to grow. So we sort of see 2008, we have 250,000 entries. By 2012, we have 400,000. By 2016, we have 700,000, and so on. This shows the increase in load that would happen as a result of virtual aggregation using routers that have only 240,000 FIB entries today. And you can see that it's completely negligible until about 15 years out, and then it starts to grow. So, I mean, I think the bottom line is that you could actually deploy this, shrink your FIBs, extend your router life for years, really, and pay very little penalty in doing that. So if you want to work with me, please let me know.
Very quick questions? No? Okay, well then we have Alain.